it's Chris, and now we're going to get into some calculations for this bungee jumping physics problem. So for part F, it says focus on this instant of greatest tension and starting from a fundamental principle, determine the spring stiffness for each of the two chords. Okay, so before we can start to do these calculations, ultimately what we're going to have, and I'm going to maybe zoom in here and draw just like a tiny free body diagram, but basically, so if this is our bungee jumper, we're going to have a downward force of mg and then an upward force of kx for each cord or spring that's pulling the bungee jumper up. And so let's see if we can color code this a little bit. But basically what's going to happen here is that our net force at any given point in time is going to equal whatever that distance is, or whatever that difference is rather. And so here you would have your two spring forces minus your mg, and your net force is always equal to mass times acceleration. So we'd have 2 kx, those two springs, or those two chords, minus mg. So those are the equations that we're going to be looking at here. And we can see in the question that they want us to determine that value of k. And in order to do that, we have to have a few other values. So in order to solve for that, we need to know the mass, which we do. We need to know g, acceleration due to gravity, which we do. We need to know displacement, x, which we do at that point of maximum tension. And we need to know acceleration of the system, and that we don't know at the moment. So before we can solve for k, we need to find our acceleration at that moment. And let's take a look at how to do that. So we're going to break this up into two different phases. So first, just like we did at the beginning of the question, when in part A they asked you to break it up into these different kinds of diagrams, we're going to look at a few of these. We're going to start with one. Let's see what happens before those chords even begin to stretch. So the chords themselves are going to be 13 meters in length, which means we're going to be a free-falling body for those first 13 meters. So in order to find that acceleration that we need for F, let's see if we can figure out what that would take. And to do that calculation, let's look just at, I'm going to maybe move over to a blank page here so that we can, let's find some blank space down here. And let's just do this calculation. So again, we're going to kind of clean it up a little bit. Here we got our platform, our bungee jumper. Just going to leave the platform, and we're going to go 13 meters down from this point to this point, 13 meters as a free-falling object. So let's see what kinds of values we could use and what sort of equations we can use in order to identify what's happening with our bungee jumper at that point in our fall. So here we're going to have an initial velocity of 0 the moment we step off that ledge, right? And then we're going to have some sort of final velocity that we don't know yet. That would be helpful to find out. We know for this portion that we're going to have an acceleration due to gravity of 9.8 meters per second squared, because we know our value of g on Earth. And then we know that this value of 13 represents our displacement along that y-axis. We can call it delta y. So let's see what equations we can use for that. And hopefully we know our, I call them the big three, but hopefully we know our big three velocity equations, which is going to be your final velocity is equal to your initial plus at, acceleration times time. We don't have time here, so that one might not work for us. And then we also know that we can get a displacement, or delta x, and it could be delta y. We call delta x displacement as our standard way of representing it, but I like to use delta x versus delta y so that I can represent which axis I'm looking at, and that would be v naught t plus 1/2 at squared. So again, great equation, but doesn't help us here because we don't have time. But we do have your final velocity squared equal to your initial velocity squared plus 2a delta x, and this equation doesn't require time. So we actually have all the components to utilize this. And so of our big three, that's the equation that we'll use here to find that final velocity. So here we'll have v final squared equals our v initial, which was 0, squared, plus 2 times a, our acceleration due to gravity, which is 9.8, times delta y, which in this case was 13 meters. And when we plug that in and do the math on that, so we're going to have v squared equal to 0 plus 2 times 9.8 would be 19.6, and 19.6 times 13. That one I don't want to do in my head, so let me go ahead and calculate that. 19.6 times 13 is going to be 254.8. And when we take the square root, we get a value for v final of 15.96. So that's how fast we're moving when we get to this point in our jump. So it's a helpful piece of information, but we're not done quite yet. So here we've added this to what we know. But remember, we're still trying to find acceleration of the system. And let's see at which point we're trying to find acceleration of the system. Because here I'll leave that value so that we can see it, but I'm going to just redraw our scenario. Bungee jumper is going to jump. And then we get 13 meters down. And that's when the cords, right, the two cords are going to start to stretch. And then they're going to stretch another 22 meters. So here they start to stretch at this point, and then they stretch another 22 meters attached to our jumper. We'll represent as a box here for our free body diagram, but basically what we're going to see is that for this second phase here, when we get to this point, remember we said that we have a v final at this point of 0. Now we can treat this like it's a second problem. So we're going to use this value of v final from that first part of the jump. That's really going to be our v initial for this second part of the jump. That's how fast our initial velocity is when those cords start to stretch. So here, this v initial will be 15.96 meters per second. And then v final at the end of that stretch when we're at max tension, right? Because this is our goal here. This is our like target point that we're talking about in the jump, is when we have those cords maximally stretched out. And that's going to be with a v final of 0 at that moment. So that's enough for us to figure out our v initial and our v final. And then we still know our displacement. So if we are trying to find our acceleration of the system, then here we can use this equation again, but we're going to have values in some different places than we did originally. Here v final squared is 0 squared, v initial squared is 15.96 squared. And then we have plus 2a. And our delta y in this case, that's over the course of 22 meters that we're slowing down that much. So basically what they're saying in this calculation is that we have the spring force opposing our downward motion, which is slowing us down. So we're actually going to be accelerating in that opposite direction. If we do this calculation here, we would get 15.96 squared, which is 254.8. So we would get 0 equals 254.8 plus 44a. Subtract 254.8 from the other side. You'll see that we're going to get a negative acceleration here, which means that we are decelerating. We are accelerating in the opposite direction. Because of those cores, because of those spring forces, we are being pulled upwards. So here 254.8 divided by 44 would give us a value of negative 5.79 for acceleration, which means that we are accelerating 5.79 meters per second squared in the upward direction. That's all that negative in front means. It just tells us that it's opposite direction. So we're moving down, but we are accelerating in that upward direction. And that's the value, negative 5.79, that we can use for A here. So if we are treating the force in the upward direction, which would be our spring force, if we want to treat that as positive, then we can plug in 5.79 for A. So this calculation, when we plug in those values, will be our mass, which was 120 kilograms, times our acceleration of 5.79, and that would be equal to 2k times x is our displacement. And remember, it's displacement from equilibrium, so it doesn't include the total 35 meters below that platform. It's only going to be the stretch, which is 22 minus mg. And so now we can see that we have enough to actually solve for k in this question. And to do so, we're just going to plug in and rearrange. So here, this would be 694.91 equals 44k minus 120 times 9.8 would give us 1176. We add that to the 694.91, giving us 1870.91 equaling 44k, and we divide by 44, and that would give us a spring constant here of 42.52. And for our purposes here, I'm using a phone calculator, so some of the rounding might be a little bit short. Make sure that you factor that into whatever your specific assignment requires in terms of number of decimal places. But 2 decimal places is about all I'm willing to do when messing around with the calculator on the phone. But that would give us 42.52 as our value for Ks. Now up next, we're going to get into the last few parts.